So for this question, you're asked to draw the major E2 bimolecular elimination product. So the issue that you need to figure out here is the orientation required for elimination, and that is best using a Newman projection. So what you want to do is basically put your eyeball looking down that sigma bond. So that's going to be your front carbon. And so if we do that, if we start drawing that, we have the phenyl group up, we have hydrogen over here, and we have methyl over here. Then our back carbon, we're going to see that the tert-butyl group is down. The bromine is on the same side as the hydrogen, and so the hydrogen on the back carbon is on the same side as the methyl group. So again, we're looking down this bond. That's the sigma bond we're looking down. And so when you're doing an elimination, so that E2 bimolecular elimination, you need an anti-periplanar orientation of H, C, C, X, which is the leaving group. That is the sigma bond you're looking down. And so what do I mean by anti-periplanar? That means in the Newman projection, so you have your H, carbon, carbon, and then your X group. So that's 180 degrees. So this is where the Newman projection comes in handy, because you have to achieve that anti-periplanar orientation, and then when you do, you can do the elimination, and it's going to tell you the geometry about the alkene product. So what we need to do is orient this H and this Br 180 degrees. So what I'm going to do is I'll just rotate the back. I'm going to rotate the back. So rotate. I'm going to leave the front carbon as is. So I need to do a rotation that places the bromine here. That's going to place this hydrogen down, and then this tert-butyl group over here. So the base, just B, supplying the electrons. It's going to abstract. It's going to eliminate. So we lose the conjugate acid, so we'll say this is plus, Br minus, that salt is the byproduct or coproduct. And so when we do that, this gives us the orientation that the phenyl group and the tert-butyl are on the same side. The H and the CH3 are then on the same side of the alkene that's formed. So we could do a Newman projection of that as well. You're allowed to do that. So with the front carbon, I'm going to say PH, CH3. The back carbon, we have the tert-butyl group there, the H there. And so this is going to be equivalent to CH3. Then we said the tert-butyl group was on the same side as the phenyl group, then the H. So you have a constitutional isomer. So it looks like what you've drawn. If we assign EZ, so on this side, this would be the number 1 priority. And then on this side, this would be the number 1. So you have, it looks like the E, and the correct answer is the Z, is the major. And again, that's due to the Newman projection. So in this question, again, you're doing an elimination. So for methyl chloride, you're only observing one elimination product. So what do you need to do to solve this? So you identify, that's the good leaving group. That's going to be part of the elimination. So if we call that the alpha carbon, the carbons bonded to that are beta, and then we have beta prime. So there's two of them. So the issue here is you have to evaluate both. And the question is, which one of these is going to give you the HCCX anti-periplanar. So this is when you're doing eliminations, that's the geometry you need, and that's where these Newman projections in chair conformations come in handy. So when you're given a flat cyclohexane, you absolutely must convert it to a chair. So I know it's sort of disconnected from when we learned it in the prior chapter, but this is when it's coming home to use, actually. So we need to convert this to chair. And when we do that, so the chlorine is down. I'm gonna put it down. Then this isopropyl group next to it is up. So this hydrogen has to be equatorial. Then we have H, and then next to that we have H equatorial, CH3 axial. So in this conformation, I'm going to outline in green highlighter here this H. In that conformation, that is the correct orientation for an elimination. So if you were to look down, this sigma bond, you would see that this HCCCl, that's 180 degrees. That's what you need. But you're not done yet, in the sense that you do have to do a chair flip to see if the other beta carbon places the HCCCl in the same required orientation. In this case, it won't, because that chlorine is axial, and when you flip it, it's going to go equatorial, and it will not achieve the required anti-periplanar conformation. So all I'm doing now is a chair flip. And we can see that this chlorine is no longer axial, it's equatorial. So this conformation is not going to be reactive. This is the only reactive conformation, and the stuff I've highlighted in green shows you where the elimination is going to occur from. So in your answer, the alkene is in the wrong place. So if we convert this to the elimination product, we're going to get the following. And so when we draw that in flatland, we have the isopropyl group still up, the alkene here, and then the methyl group down. So you have to be aware of the flat cyclohexane has to be converted to a chair. Then you're examining beta, beta prime, and any other beta carbons for this specific anti-periplanar relationship. So here we have the neomethyl chloride. This is a diastereomer of the methyl chloride. We'll do the same thing and convert the flat cyclohexane to the chair. You can see now that the chlorine is equatorial, so we have to do a chair flip to get it axial. That's required. So we're going to do Oop, we don't want that arrow. We want chair flip. So when we do that, the chlorine becomes axial, isopropyl group becomes equatorial. We have our H's at this beta carbon. The methyl group is now equatorial. And so here now, again, here's beta, here's beta prime. I'm using those because they're different groups. For example, this is a methine, this is methylene. So beta is not equal to beta prime. But now the choice you have to make is, here's the chlorine is axial. And so if we go this way, we see that's also anti-periplanar, but we can go the other way as well. That's anti-periplanar, so you can actually get both elimination products. So one issue in your answer is that you've drawn one of them where you've eliminated this H because the alkene's going next to the isopropyl, which you have. But when you're at an sp2 hybridized carbon, you typically do not show wedge or dash when you're at sp2. So the better way of drawing that one is the following. So you're keeping that everything's sort of in the plane. So if we were to eliminate from here, then you would retain the stereochemistry of both of those stereogenic carbons. So the elimination is here. And so those would be the two products expected for this one. The main issue with this problem is in your answers is basically this one is correct, these two are not, because notice how you have 2 alkenes. So here you've only had one, so you have to retain the other one because they're resonance forms. So this should be pi bond CH2. This should be pi bond CH2. So your major product is correct. And again, this results from E2. So when you're in the elimination manifold, you have to consider geometrical isomers. So you've drawn, again, if we consider which one this is the number 1 priority here. This is the number 1 priority. They're apart from one another. So that's the trans, or we would say E. So a minor product would be the Z or cis. So this, again, this would be a minor product. So those are di-substituted alkenes. You can also eliminate from the methyl group. So again, this has to do with, there's your alpha carbon. You have a beta carbon, and then you have another beta prime. So when you're eliminating from the more substituted carbon, you get the more substituted alkene. If you eliminate from the less substituted beta carbon, you get the less substituted, so that's also a minor product. So this is mono-substituted, so there's no EZ. And then the final product you can get is substitution. So this would be for OH, which you've drawn, but you have not indicated stereochemistry. So this occurs with complete inversion. So the tosylate gets displaced by hydroxide from 180 degrees. So that's how you end up with that dash stereochemistry. So for this one, the really glaring issue that I see is you are starting with, so this is non-chiral, and then you're indicating chirality there. So again, methyl, methyl, that's the same. So there's no point in putting a wedge or a dash. The other thing is this is ethanol as your solvent, and you have OH. So both of those should be condensed into this as the substitution product. So again, keep in mind when you're doing this, you have no form of hydroxide in here. This OH, the H goes away, the oxygen's still attached to the ethyl group. So that's your substitution. You can also get elimination products from this. So again, here's your leaving group. You have beta, those are equal. Then you have beta prime. So if you eliminate from beta, you would get the following disubstituted alkene. If you eliminated from beta prime, you would now get trisubstituted. So those would be the SN1 manifold, and then these would be the E1. And again, the 1 is because it's unimolecular, and that's because you have basically a polar aprotic solvent. This ionizes to a carbocation. So when that happens, the carbocation can then achieve formation of these through basically a bifurcation of the manifold. So again, when you're thinking about reactions, the reaction coordinates we've looked at have been like a slice, but really they're sort of like a mountain range where they're 3D. So if this is this is an intermediate sitting in a well, it can go any sort of path. This is the SN1 path, this is the E2 path, and then from there it can get these different isomers based on the elimination from beta or beta prime.